Audio Jungle. Audio Jungle.
So now we'll talk about the types of ideal flow. Yes or no? Types of ideal flow. What this ideal flow also called? It is also called potential flow. What is this potential flow? What is this potential flow? Potential flow is steady, then incompressible, and then irrotational. Okay, called potential flow, steady, incompressible, and irrotational flow called potential flow, and this potential flow also called as ideal flow. All right. Now, till now, we all know what is the steady flow. We all know what is the incompressible flow. We all know what is the irrotational flow. In fact, all the concept of velocity potential function, streamline, equipotential line, okay, and streak line, path line, timeline, all the things we have seen. So now this is the time to go for the next level, which is related to the types of ideal flow. And in ideal flow, you have heard during your graduation BTech that type of ideal flow, like uniform flow, okay, parallel to x-axis, parallel to y-axis, then source flow, right, sink flow, and vertex flow. In the vertex flow also two types, free vertex and force vertex, okay. Doublet flow, that is the combination of source and sink flow. Rankine half body, Rankine full body, and cylindrical flow, non-rotating cylindrical flow, rotating cylindrical flow. So all this type of flow we have to cover in this types of ideal flow. All right. So here in types of ideal flow, if you talk, number one, uniform flow, okay. Source flow, sink flow, vertex flow, okay. So these are the what types of the vertex flow. Doublet flow, okay. And okay, that much of that types of the flow we'll talk, then we'll superimpose that. In fact, doublet flow also is the superimposition of source and sink, but basic, you can say this is the basic type of the flow. Then we'll superimpose with, like, we'll take the combination like uniform flow plus source flow. Then there will be one another type of flow called Rankine half body. Then we'll take the combination called uniform source and sink called Rankine full body or oval body flow. Then we'll take the combination of this flow with the vertex. Then we'll take with the doublet. So all those things will come one by one. Better I will give the combination here. So that is also 1 mark question. So one by one we'll see. So you check like superimposes. We'll give the heading superimposed. Superimposed flow. Superimposed means it is the combination of more than one. More than one in the sense one will take one combination called uniform plus source. If you are taking uniform plus source, this is called Rankine half body flow. 1 mark question they can ask from the superimposed flow. Okay, you have to take combination of uniform flow plus source flow plus sink flow, then it is Rankine full body flow. Okay, Rankine full body flow. That is also called sometimes oval body. What it is called? Oval body, like egg shape. Oval body in the sense like egg shape, no? Not exactly circular. Oval body means it is like a egg shape. Okay. So two types of the flow I have told you: uniform flow plus source flow. Then uniform plus uniform flow plus source flow plus sink flow. Then it comes one kind of flow called Rankine full body flow. Okay. Then we'll have a source plus sink flow. There is a special case. One special case I will tell you, it is called doublet flow. It is called doublet flow. Just listen carefully, you will understand. It's very easy only. Okay. Uniform plus source, Rankine half body, uniform flow plus source flow plus sink flow. It is called Rankine full body flow. Source flow plus sink flow, but one very special case. Okay. And that special case I will tell you. Then it is doublet flow. All right. So doublet flow. Now we'll go for the uh, uniform flow plus doublet flow. Okay, uniform plus doublet flow. It is called circular flow. What it is called? Uniform plus doublet called circular flow. What it is called? Circular flow. But it is non-rotating flow. Okay, circular flow or cylindrical flow, and it is non-rotating cylinder. Okay, then one combination will have, which is called uniform plus doublet plus vortex flow. It is called rotating cylinder. Okay, called rotating cylinder flow. So these are the like types of the superimposed flow. Understood? Types of the superimposed flow. It is very special, and they are asking question from here. Okay, question they are asking from here only. So This is very special, as I told you. This is called superimposed flow. So actually doublet is also the kind of superimposed flow. Okay, so better we'll remove from here. All right, now basically we have uniform flow, source flow, sink flow and vertex flow. Okay, so doublet is also superimposed, so I have given here only. Here I have given, so you can connect from this. Okay, so first we'll see one by one what is the source flow, what is the uniform flow, what is the source, what is the sink. Then we'll go for the combined flow. I mean, we'll go for the superimposed flow. One by one we'll see. All right. So elementary potential flow you have seen. It is also called elementary potential flow. This one, no? This is what? This is what? Elementary potential flow. Okay. So, but as I mentioned you, it is the very special case. That is special case I will tell you. So here I am writing this doublet flow. So this is called what it is called elementary. Why I am writing this doublet flow in category this elementary flow? I will tell you. This is the elementary potential flow, elementary flow or okay. Among this source flow and sink flow, that separate I have written. Actually you can give source and backslash sink, you can say. So basically elementary flow you have one, this is one, this both combined are one, it is now two, this is what three and this is what four. So how many elementary flow we have? Four elementary flow we have. Source and sink both are like exactly just opposite, but it is same, just opposite and same. Okay, magnitude wise also it is equal and opposite, no? So source by word only you can understand. Source means going away, sink means going inside. That's the only difference. The rest everything will be same. So I'm considering both flow combined, not combined, but both flow I'm considering as a one single flow. So 1, 2, 3, 4. Why doublet flow I have considered as a elementary flow? Because doublet flow is the one special case. And what is the mean of elementary? Elementary means with the fundamental flow. Okay, fundamental flow. Elementary flow means it's a kind of fundamental flow, and fundamental flow in the sense with the help of these all four types of the flows. With the help of these four types of flow, we can develop any different type of flows, like superimposed flow. Rankine half body, Rankine full body, circular, rotating cylinder, non-rotating cylinder. So others flow we can generate with the help of these elementary flow. That's the fact of it. Okay, done. So now one by one we'll start. First we'll go for the uniform flow. Okay. So first we'll take uniform flow. Uniform flow. So what is the uniform flow? See, by the definition, actually uniform flow is the flow where the velocity is what not going to change with respect to the distance. It is not going to change with respect to the place, or it is not going to change with respect to the length or distance. Means in x direction if flow is there, so in x direction from 0 to infinity, that velocity will be constant in x direction. That is the uniform flow. Similarly, you can define as a y direction also. If it is in y direction also, if the velocity is not going to change, then it is called uniform flow. Okay, so basically uniform flow you have to define in two ways. One, it is called uniform flow parallel to x-axis, uniform flow parallel to y-axis. Yes or no? Now from last class, few lectures you have seen related to line stream function and velocity potential function and equipotential line. There you have seen whatever the flow we are showing, direction of the flow, it is actually streamline. Yes or no? Equipotential line, as I have explained, equipotential line will not have direction. There is no direction for the equipotential line. You can say it is blind. Nah? Equipotential lines are blind, but streamlines are having eyes. They can, you can say, they can see like where is the direction of the flow. They will tell you. They know very well wherever it is going. It means the direction of the flow is there. So direction of the flow will be indicates with the help of streamlines, you can say. Okay, if I am showing, suppose just for example, if I am saying this is the streamline direction, so you have to say this is the direction of the flow, because that is the definition of a streamline, right? So right. So now wherever I will draw the line, so for the direction of the flow, that means it is streamline. Okay, and along the streamline, you know the definition. Along the streamline, stream function will be constant. That you have seen. That is the definition actually. Yes or no? Now, so uniform flow, first we are going to talk about uniform flow parallel to x-axis. Now, number one, we are going to discuss uniform flow, uniform flow, uniform flow parallel to x-axis. So how you will define? Definitely you will draw the xy plot. This is x and this is what? Y. If I am saying parallel to x-axis, it means the direction of the flow parallel to x-axis. Yes or no? It means the direction of the flow will be parallel to x-axis. So I can show this is the flow parallel to x-axis, but directly I can tell you parallel to x-axis is the direction of the flow, but first we'll write the mathematical formulation and then we'll draw, so that will be better for the understanding. Okay, so I'm considering that velocity which is uniform or constant along x-axis, and it is nothing but capital U. Actually there are the components of the velocity. Okay, there are the components of the velocity in x direction. Okay, I will draw the axis also better. In x direction and in y direction. In y direction, what is the velocity component? It is v. In x direction, what is the velocity component? It is u. So if I am saying parallel to x axis, so that flow will be in x in direction of x axis only. There is no flow in direction of y. Yes or no? So can I say in x direction what is the velocity component? It is u. So in u I will write capital U. Okay, means there is the velocity which is in x direction, but what will be the another component v? In y direction it will be 0. Why it is 0? Because flow is what? Parallel to x axis we are taking. So I will write here, so it will be more clear to you. What is u? So what is u? U is basically, I must write velocity which is uniform, which is uniform or constant along x-axis. So it means x component will be small u, so velocity capital U will be there, and in y direction velocity component will be b, so here direction y direction velocity will be 0, because you are talking about the uniform flow parallel to x axis you are talking. Okay, for that reason only small u will be capital U, and capital U is the total velocity along the x axis. Okay, fine, this is the one thing. Now we want to draw the plot, so how you will draw? So first 2 3 graph I will tell you in detail, and for rest we can draw directly. So how to draw it? So for that, you, because if you want to draw the direction of the flow, so there will be a streamline, so you have to relate it with the stream function. So what is the stream function? It is u is equal to what? Dou psi by dou y. What is v? Dou psi by dou x. Nah? One is minus, one is plus. Yes or no? If you recall it, so this is the minus, anyone you can take minus, doesn't matter. Okay, now what is u? U is nothing but capital U, dou psi by dou y. What is the small v? It is 0. Okay, so if this value is what, 0, then it means what it indicates, dou psi by dou x is what, 0. So once you, if you integrate it, then psi is equal to what? Constant along x direction, na? Because this derivative is what? X, so it is constant along x direction. I think it is clear to you. And what about this derivative? This derivative will u is equal to dou psi by dou y, right? Then what will be the value if you integrate it? So what you will get? Simply you will get psi is equal to, you will get u y, yes or no? U y, this is the thing. Again, if you want to add constant and all, you can add also, no problem, but this is the final result. In short, I am telling, I am not going to give, I am not going to take more time here. In short, I will finish the first two plot. I will show the exact mathematics formulation, and all rest we can draw directly. So psi is equal to what? You will get uy. I mean, uy means y, if you are changing psi value, you will get different value you will get. But what about in x direction? Whatever the in x direction, if you go, psi will be constant. That's the mean of it. Okay, so this is what is stream function. This is what relation for the stream function, and with the help of this stream function you can draw a streamline. Now we'll go for the potential function. What is the potential function? Potential function, you know, u is equal to dou phi by dou x, and v is equal to dou phi by dou y. What is u? It is capital U. What is the phi? Phi is nothing but ux, and here v is nothing but what? 0. You will get phi is equal to constant along y direction. Yes or no? So now both you got, I mean, streamline and potential. This is what equipotential function. Phi is what? Equipotential function, or sorry, potential function. If you know the equipotential function, then you can draw equipotential line. Yes or no? Now we'll draw it. Check. From this you can say phi 1 is equal to ux1, phi 2 is equal to ux2. Yes or no? phi 3 is equal to ux3. All right. Similarly, stream function, this psi, for the psi what you can write, for this psi what you can write, psi 1 is equal to uy1, psi 2 is equal to uy2. Similarly, psi 3 is equal to uy3. Yes or no? Now I will draw it, this graph parallel to x-axis. So parallel to x-axis, there was the, we had defined parallel to x-axis, and we had said parallel to x-axis velocity is what, suppose, and we consider velocity is what, u. In y direction there is no velocity. Now I just want to show you the potential line, equipotential line and streamline, how to show for the parallel to x-axis. That is the main point, right? So how we will show it now? Different diagram, color if I will take, then it will be more clear to you. You got a streamline and potential line both. Okay, so streamline you got, if this is what y and this is what x. What you got is streamline, psi 1 is equal to u y1, y1, y2, y3. So y1, y2, y3 you are getting in y direction. If y direction, if you are changing, you are getting psi 1, psi 2, psi 3. So it is like, all right. So psi 1 means what? Psi 1 is equal to what? U into y1. Psi 2 is what? U y2. Psi 3 is what? U y3. Yes or no? Check this streamline. You got this result, right? Psi is equal to uy. So y1, y2, y3, this change in y you will get in y direction. So if you are changing y value, because u is the constant along x-axis, u is not going to change. So y1, y2, if you change, then psi 1, psi 2 you will get y3, psi 3, y4, psi 4, because u is constant. So this is the streamline. Now check about the potential line. As I told you, equipotential line don't have any direction. But one thing you have proved in last class, equipotential line and streamline both are perpendicular to each other. So streamline direction you have seen here, I have shown you. This is the streamline direction. So where will be the equipotential line? Just perpendicular. That is the one thing you have proved in last class. But now from this formulation, what you are getting? You are getting u phi is equal to ux. If you are changing x, then you will get different, with the different value of x, you will get different value of the phi. Phi is the potential function or velocity potential function, right? U is a constant value, it is not going to change. So x1, x2, x3, x4 means phi 1, phi 2, phi 3. If you are getting different value of x, it means you are going to change that value in x direction, x1, x2, x3. I will show in diagram, so it will be more clear to you. So suppose this is the x1 value here, and perpendicular you have to draw. This is x1, this is x2, this is x3, this is x4, and this is x5. Yes or no? Right? Now based on this you can write, this is what? Here I will write, anywhere you can write phi 1. This is what? Phi 1. What is the phi 1? U x1. What is the phi 2? U x2. Nah? So you can say this is the x1 value, this is the x2 value, this is the x3, x4, x5. So phi 2, this is what? Phi 3, this is phi 4, and this is what? Phi 5. Yes or no? What is the phi 1? Just formula you check u x1. What is phi 2? U x2. What is phi 3? U x3. And what is phi 4? U x4. So basically this is the pattern when the flow is what? Parallel to, okay, parallel to, flow parallel to, flow parallel to, parallel to x-axis. When the flow is parallel to x-axis. So guys, now all these things, like here we have drawn, okay. So all these lines are streamline. Yes or no? And all these lines equipotential line. Equipotential line. So I think now it is very clear to you, like if it is parallel to x-axis, then how to draw the streamline and potential line, right? Similarly, you can do for the parallel to y-axis. Now, parallel to y-axis, you can draw by your own, just like I explained parallel to x-axis. So similarly, you can do parallel to y-axis also. Okay, I'll show you. So here you can give heading second number, uniform flow, uniform flow parallel to y-axis. So if it is parallel to y-axis, so again you have to check axis system. This is x. In x direction, what is the velocity u, and in y direction, what is the velocity v. If it is parallel to y-axis, and I am considering parallel to y-axis, that flow is nothing but capital V. So here I can say u will be 0. Why? Because it is not parallel to x-axis, it is parallel to y-axis. If the flow is what parallel to y-axis, it means in x direction there is no velocity component. Hence u will be 0 and small v will be capital V. Why small v is equal to capital V? Because small v is the velocity component in y direction, and in y direction velocity component is what? V. Okay, so again you can perform the same thing, stream function and potential function formula you can perform, but I am not going to do it because it is not required. I will directly draw the pattern. So this is the flow pattern when flow is what? Parallel to y axis, x and y. Flow parallel to y axis means this will be the streamline, and this will be the streamline, and this will be the equipotential line. This will be the equipotential line. Yes or no? Everywhere it is perpendicular to each other. Okay, so here you can write this is what? Psi 1 is equal to what? V x1. Psi 2 you can write V x2. Psi 3, Psi 4 and Psi 5. Here you can write phi 1 is equal to V y1, phi 2 is equal to V y2, phi 3 is equal to V y3, and phi 4 is equal to V y4. Okay, it's very simple. So this is the flow pattern. Okay, this is called flow pattern. Flow pattern. Okay, how you will get this? Again, if you do the same thing, that derivation you have to take. This is for the potential function, this is for the potential function I had done. So you write the formula. Instead of u will be 0, now you will have a capital V. If you differentiate, then you will get that. Okay, and this was the stream function. Okay, so if this formulation you perform for the this second case also, okay, for this also if you perform, then you will get that result. I will write here what is the result if you perform the stream function and potential function. Then what is stream function you will get? You will get stream function psi is equal to, you will get Vx. And what potential function you will get? You will get potential function Vy. Okay, if you do this, then this result you may get. And now for different value of x1, x2, x3, x4, you will get this flow pattern. Hope you understood. So this is the like flow pattern for the streamline and equipotential line. Okay, if it is like what is the uniform flow parallel to y axis, so this will be the flow pattern. What will be the flow pattern for the uniform flow when parallel to x axis? That already I have derived well. So in this way you can get idea at least. Okay, and always remember the streamline and potential line, equipotential line, will be perpendicular to each other. Okay, so all everywhere all each corner you can get, this is what 90 degree na, everywhere wherever it is crossing to each other, it is 90 degree. Now one very special question they are asking from the uniform flow. What will be circulation for uniform flow? Okay, now check, I'll give the, this is now the uniform flow. Okay, this is very nice question actually. Now this is the uniform flow. See, this is the uniform flow. I must say here the for this uniform flow, velocity is what I am considering v infinity. Okay, now they are saying calculate what is the circulation for the uniform flow. So for the circulation, we know what is the circulation. What is the circulation? What is the circulation? So circulation we already have seen in last class. It is the line integral of closed contour, line integral of tangential velocity. Okay, tangential velocity. Okay, so v vector into ds, or you can say once you solve it, then you will get v ds cos theta. You may get, this was the circulation. So first for this uniform flow we have to design one closed contour. So we'll design one closed contour. I am considering a rectangular closed contour. This is the rectangular closed path. Here we need to calculate the circulation. Okay, now I think this hash line is what confusing us, so better we'll remove this hash line. There should not be any confusion, right? Fine. So now we are having points A, B, C, D. So basically they are asking what is the circulation A, B, C, D. What you can write? AB, circulation for BC, circulation for CD, and circulation for DA. Agree? All right. Now I can say here the whatever the fluid element you have taken, length here for this fluid element is what? This side it is A and this side it is B. Alright. Now if you check A to B, for A to B, that velocity component is V infinity, and if you are going for the going to calculate circulation for AB, so AB is just along the flow. AB side if you check, okay, it is along the flow. So if check the tangential angle, so tangential angle will be what? Theta will be what? 0. But for BC, what will be the BC? BC is what you are going B to C, means just perpendicular to the direction of the flow. What is the direction of the flow? This is the direction of the flow. So if you are going perpendicular to the direction of flow, so this tangential velocity will be perpendicular to the BC actually that time. So theta will be 90 degree. Similarly, if you go for the C to D, so same thing you may have, but theta will be, here you have taken A to B along the flow, but if you go C to D, then it is opposite to the flow. So opposite to the flow means it is 180 degree. Similarly, we can go for D to A. So again it is theta, and that will you can consider it is 90 degree. Okay, or you can add 180 plus 90, 270. 90 or 270, it's your choice. Whatever you can take it. Right? This is the angle now. Now if you go for the circulation of AB, so you have to write V ds cos theta. This this is the formula now. Now if you go for the calculation, so you are going to calculate A to B. If you are going to write circulation AB, so you are going to write A to B. Velocity is what? V infinity. What is the ds? Ds is the length in AB. What is the length in AB? It is A. So you can write V infinity A cos, angle already I have written separately, it is 0, cos 0. So if you check here, so it is nothing but V infinity A you may get. Alright, cos 0 is 1, and integration A to B is showing like from A to B you are going, side A to B you are traveling. That's the mean of this integration. No? There should not be confusion. A to B means you have started here and you are going to end at this point, because it is limit, right, in integration A to B. Now you are going to write BC. So circulation BC, again the same formula you may have. Now you are going B to C. Velocity is what? V infinity. What is the side? Check. This side you have taken B here, na, B to C. It is B. So V infinity B cos 90. Cos 90 is what? 0. So here you will get 0. Similarly, you go for CD. So it is CD. So obviously V infinity, what is the CD? CD is the side is A, and for CD what is the angle? 180. Side is A and cos 180. What is cos 180? It is minus 1. So you will get V infinity A in minus. Similarly, you go for D to A. Okay. Now you can write V infinity A. Sorry, side is nothing but D to A. What is the side? D to A, it is B. It is B. Angle I told you, it is 180 plus 90. If you write 270, or it's your choice. If you are writing 270 also. What is the cos 270? Let me check. It should be 0, right? Because 0. So this is nothing but again 0. So what is the total circulation? A, B, C, D, A. What is this? whole is what? 0. What is the mean? What is the conclusion of it? What is the conclusion of it? It's very important actually. So conclusion is very clear. For the uniform flow, anywhere, if it is uniform flow, anywhere in the flow field, if you are going to calculate circulation, you may get 0. If circulation is 0 means what? Verticity becomes 0, angular velocity becomes 0. That already I have explained to you. Always remember, they will ask to you for single marks. Circulation for the uniform flow. So how to solve I have explained you, but only you need to remember circulation for the uniform flow will be 0. Okay, this is very important actually, and it is for what? It is for uniform flow. Okay, and if circulation 0, what it indicates? Omega 0, or you can say zeta 0, or you can say angular velocity 0. What it indicates means irrotational. Understood? And if you check there, in starting only this uniform flow, what you considered? See here, what you considered? You considered ideal flow, and for ideal flow, what was the third assumptions? Irrotational. Still, already you have considered ideal flow, and you are talking types of ideal flow like uniform flow, source, sink. So that uniform flow itself, it is ideal flow, and ideal flow means itself it is a potential flow, and if it is potential flow, it means itself it is irrotational flow. And if it is irrotational flow, so it is a very nice conclusion, you will get circulation 0. There is no doubt about it. So directly you can hit the answer if question will be asked to you, and they will ask to you. Okay, this is very patent question. For one day exam they are asking, what is the circulation for the uniform flow? Alright, so here even you have proved also. Okay, just for your understanding I have proved here. Directly also you can hit, no problem. Okay, but it is very patent question here. Anyway, so till now you have seen the uniform flow, parallel to x-axis, parallel to y-axis. Alright, sometimes it happens that flow is maybe inclined. That flow may be inclined to the both. Okay, if it is inclined to the both x and y, then what is the mean of it? Doesn't matter if you are considering circle or if you are considering here triangle also. Okay, whatever the circulation you will calculate for the uniform flow, if it is not a rotational flow, okay, or if it is not a circulatory flow, if you are going to calculate that flow is what? Uniform, then you may get that circulation will be 0, because already you have considered this is the kind of ideal flow, and ideal flow means it is irrotational flow, already you have considered. So doesn't matter you are going for the triangle or circle calculation, okay, it will be 0, because your first assumption was ideal flow. You are talking this calculation for the ideal flow. All the type of flow you are going to study, vertex, doublet, uniform, parallel to x-axis, parallel to everything, it is ideal flow. Ideal means potential flow. Potential flow means irrotational flow. If it is irrotational means what? It is not rotating about its own axis. So already it becomes 0. So circulation no need to calculate, it becomes 0 only. Understood? Yes or no? Your assumption is like that because you are talking about ideal flow. So ideal flow itself irrotational flow. Hope you understood. Now, now you are going to talk parallel to x-axis is done, parallel to y-axis is done. Now you will write uniform parallel flow under an angle. Okay. Uniform parallel flow under an angle alpha. Means still it is a parallel flow. Okay, it is not like a zigzag flow or something, it is parallel flow, but now it is an angle. Okay, so I will draw the lines so you may understand. So again I just like, because everything I cannot derive because of the time constraint, so few things you have to adjust, few things I will give direct result also, that you have to try to understand. Still, if you are facing problem, you can ask also, no problem, but I will avoid all the derivation. Okay, that's not possible actually because of the time constraint. So this is what x axis and this is what y axis. Now still it is a uniform parallel flow, so I will draw parallel flow, but it is at an angle, so I am considering it is angle with the x axis. So now my flow will be like this. See, this is parallel to x, sorry, still parallel flow, uniform parallel flow, but at some angle. So I am saying this angle is nothing but alpha. Okay, just say this velocity is nothing but, you can say u. Okay, actually it is not exactly u is always parallel to x axis, but here I am considering, okay, u, velocity u, or I say u infinity. So now there will not be any confusion. Now again, if you want to write the potential function and stream function, then how you will write? So that result I will give, just like result for the phi and psi, here I had given directly, I had given, see this result. With the help of this result, you can draw this plot. Okay, with the help of this result only you can draw this plot. How this result you will achieve? I told you first I had given derivation, proper derivation. Here I have given the derivation how you will achieve it. No? How you will achieve it for parallel to x axis. Similarly, you can achieve for parallel to y axis also, and with this result you can draw the plot. Fine. So similarly here also, for this type of flow, inclined flow, this is also called inclined flow. Inclined flow, this is called inclined flow. Okay, inclined flow. Now, so for what will be the phi and psi for this inclined flow? So write the direct result. Phi will be what? U infinity x cos alpha, y sin alpha, and what will be the uh, stream function? This is what potential function. Okay, so this is what potential function. Similarly, stream function also you can write, because for all type of the pattern flow, all type of the flow, you need to concentrate on potential function and stream function, because if you know this value, then you can plot the graph, no problem. Okay, so it will be it will be u infinity y cos alpha minus x sin alpha. Please make a note of it. Okay, so this result you need to remember. for the inclined flow, because if we can derive this also, but I will suggest don't go for derivation for all the, because it is not required. You have to remember the formula. Now how to draw the flow pattern for this? Alpha I have given, it is alpha is the inclination from the x axis. Okay, if you check from y axis, so it will be 90 minus alpha, and then you place everywhere alpha. Instead of alpha you can write 90 minus alpha. Suppose they have given flow pattern from the y axis, angle they have given from the y axis, so this formula will be valid, but instead of alpha you can write 90 minus alpha. All right, so again you can change it. Fine. Now what will be the flow pattern for this? Flow pattern means where will be the streamline and where will be the potential line. So now this is what x axis, this is the y axis. This is what alpha. So if this is what psi 1, psi 2, psi 3, psi 4. So where will be the potential function? I hope you understood now. It is just perpendicular, right? So this will be the potential function. How you would know? That property you have to use. What is the property? Perpendicular to the streamline. Simple. Perpendicular to the streamline. Perpendicular to streamline will be the equipotential line. Equipotential line, and these are the streamline. All right, streamline and equipotential. So this is what flow pattern when there is the inclined flow. So this is the flow pattern for the inclined flow. Hope you are getting this. It's very simple only. So what you got? I mean, what type of flow we had started? Uniform source. Okay, uniform flow till now. Source flow will go for the source flow, and then we'll go for the sink flow. So check. Source flow. What do you mean by source flow? By the word only you can understand. Source means what? That flow is what? Coming out from a point called source. What is the source actually? What do you mean by source? So source means the flow is coming out from a point. If I say sink flow, both we have to relate. What do you mean by sink flow? What do you mean by sink? Just like a source means the flow is what? Coming out from a point. Similarly, sink means what? That meaning is what? Flow is what? Going inwards to a point called sink flow. So the flow is going inwards to the point or to a point. So this is what? This is the point where from where the flow is what coming out. So it is like a source. So you will say this is positive, and the flow is going inwards. So it is, you can say this is the giver and this is what? Taker. Taker is always negative. No? Yes or no? So this is always negative sink. We can denote this source and sink. Okay. In very short, I am trying to finish the topic. Okay, because it's a very lengthy actually, and it will take more time if we'll go in this way. So I am trying to short out as much as possible. I am just trying from my side to short out this. Okay. So source, basically it is also defined, the source flow is the flow coming from a point and moving out radially in all direction of a plane at uniform rate. Okay, it is denoted by a q. Q is what? Discharge basically, or you can say volume flow rate. So if you are writing small q, so it will be volume flow rate per unit depth. Okay, so that I will tell you, but first you try to understand source. So if it is radially going out, and if it is coming in, so this is what? Sink flow, and this is what? Source flow. Just for understanding. Okay, all right. Now it's very simple only. Now and obviously it is radially. Okay, source flow and sink flow are radial flow. Source and sink flow both are radial flow. If I say radial flow, so what is the mean of it? Its meaning is very clear. Suppose this is circle. Okay, I can draw this radius. So along the radius, okay, along the radius, the type of flow along the radius will be radial flow, and perpendicular to radius or tangent to the circle will be tangential flow, and obviously both will be 90 degree. So for this source and sink flow, if it is radial flow, so definitely tangential component will be 0, only radial component will be there. Why tangential will be 0? Because it is radial flow. That flow is going in or going out radially, not tangentially. If it is tangential flow, it means it becomes vertex. So there is no rotation in this source and sink. only radial flow will be there, just like a sink at your home. Sink is there, right? So sink is the one example of the sink flow. That's the reason word is given sink flow. Wash basin also called sink sometimes, right? Why it is called sink? Because it is sinking the flow at one point. That will be the hole, and that flow will be going inside. Okay, got my point? So for source and sink, radial tangential velocity will be 0, but radial velocity will not be 0. I hope you understood this. Okay, this is very important basically to understand the whole concept. Now next, one more important point I just want to write here. So what is the VR? VR, I must say, it is the radial velocity of obviously of flow at a radius r from source. Where is the source? This is the supposed source. This is actually circle, but source is what? Where is the source? Source is here, O point. Here also you can consider this is O. Okay, that is VR. Now what is Q? Q is nothing but flow rate or volumetric flow or discharge. What is small q? Small q is nothing but q by T, which is nothing but discharge per unit thickness. Now I explained that day. Discharge per unit thickness or depth. What is that? It is q. And always remember, volume flow rate per unit depth, also called as strength of source. What it is called? Strength of source. Okay, it is also called strength strength of source, right? So what is the strength of source? The strength of source or sink, both I am talking. It is nothing but volume flow rate per unit depth. It is nothing but volume flow rate per unit depth, called strength of source. Okay, it is plus q for source and it is minus q for sink flow. Okay, source flow and sink flow. I hope you all understood this till now what I have explained. No? When I explained circulation, if you remember, when I explained circulation, that time one formula I explained, but circulation was related to the tangential velocity. So that time there was u theta, or tangential velocity was circulation upon 2 pi r. Similarly, in terms of radial velocity, if you remember the circulation chapter, I think last to last lecture or last lecture only, watch the recorded videos, so you will get that time I had given tangential velocity. That time tangential velocity I had given tangential velocity v theta is equal to wait, tangential velocity was circulation upon 2 pi r upon 2 pi r. Similarly, because it is the because here it is a source and sink are radial flow, not tangential. So we can relate, instead of tangential velocity we can write radial velocity, instead of circulation we can write strength of source divided by 2 pi r. Okay, so strength of source or sink divided by 2 pi r. So finally we got Vr is equal to Q upon, this is the derivation but I have explained you in very short. Okay, understood? So if there is a tangential flow like vertex and all, then V theta you will write. What is the V theta? Circulation upon 2 IR. But if there is the radial flow, just like a source and sink, then you will write VR. What will be VR? It is Q upon 2 pi R. That's all. Okay? Concentrate here. It's a very interesting thing there. One time you have to go through it properly. Next time you will understand. It's very easy only. What is the mean of it? Meaning is very clear. Radial velocity is nothing but strength of source Q divided by 2 pi r. That indicates radial velocity will be just reciprocal to the radius. Okay, if it is source, doesn't matter it is source or sink. I told you only one difference. For source Q will be positive, for sink Q will be negative. Okay, this is the source flow. I can take 2 points here. What are the 2 points? I can take point 1 and this is point 2. If I want to relate it, okay, point 1 relates to r1 radius and velocity will be vr1. Point 2, radius is what, r2, and velocity will be vr2. These are the points. Okay, what will be the relation? vr1 into r1 is equal to vr2 into r2. vr1 means radial velocity, r1 means radius. Okay, always remember, 1 marks question can be asked. Okay, and what is the conclusion point here? Conclusion is what? Radius increases, okay, radial velocity decreases. Yes or no? This is the conclusion you need to remember. Nowadays multiple select kind of question they are asking, so be aware with all these basic things. This will be valid for source and sink, valid for source and sink both. Okay, now fine. This is the till now, it's like what we have completed, it is very important. So now we need to write the equation for the stream function, and similarly we need to write for the potential function also. Okay, so equation of stream function. How to write equation of stream function? Very clear here. By the seeing this equation, we are, this is our main equation now. Okay, this is q2 pi r, and it is related to, r is related to radius, vr is related to radial velocity. So the stream function we should know in polar form, because polar form means in terms of r and theta. So we can write in polar form. What is the radial velocity in polar form? If you remember, I had given stream function and potential function both in polar form. So it was dou psi by dou theta 1 upon r. Obviously v theta will be what? Minus dou psi by dou r. But as you know, v theta is what? 0. So there is no use of it. You can say psi is what? Constant along radial. But with the help of this, what is VR? Strength of source q upon 2 pi r 1 upon r dou psi by dou theta. Take r cancel out. Take r cancel out. Yes or no? These are gone. What you will get? If you integrate, then what you will get? You will get psi is equal to q upon 2 pi into theta. Check it. Now constant and all will come. You can remove that constant. No use of it. Yes or no? What you will get? You will get q upon 2 pi into theta. This is what equation of stream function. Similarly, you have to write equation of potential function. Equation of potential function. Again, for the potential function also, it was given to you, if you remember, that polar form. Yes or no? What was the polar form for the potential function? It was in polar form, right? In polar form, it was given Vr is equal to dou phi by dou r, and v theta it was given dou phi by dou theta 1 by r. These are the, so you know this value is what, 0. So it is like 1 by r dou phi by theta, or you can say phi is equal to constant along tangential. What about here? Vr is what? Q upon 2 pi r dou phi by dou r. What will be the phi? If you integrate it, so what you will get? Q upon ln r. This will be the, yes or no? In polar form r, what is the r in polar form? Check. It is like r is what? Mod, if you write, it will be root of x square plus y square. This is very basic mathematics. And this is what? If you are writing phi, okay, just try to connect it. What is the mean of this? This is the equation of circle, yes or no? So if you draw the potential function for the source, okay, so what you will get? You may say this is what source, this is the source. So potential function will be one circle, but as I said, you are not able to draw directly. Better you draw a streamline first, then perpendicular to that you can draw the potential function. Okay, check this, what this diagram is saying. If this is the source, this is what source, right? So q upon 2 pi is constant. If you are writing theta 1, so you will get psi 1. I can say this is the psi 1. Okay, theta 1. Now another theta 2 you can say. So this will be psi 2. Psi 3. Psi 4. Psi 5. Psi 6. Psi 7. Okay. I hope you understood this, right? So this is the source. I mean, if you are changing angle, theta 1, theta 2, theta 3, theta 4, because this is what? Psi is directly proportional to theta here. Because q upon 2 pi is what? Constant. Now if you draw the flow pattern for this, how to draw? It's very clear here. This is what? Source. Okay. So from the source, that flow is what? coming out like this. If you draw stream functions, if psi is directly proportional to theta. If you change psi, so if you change the theta, psi value you will get. Yes or no? You will get like this. In short, I am trying to tell. So here I can say this is what psi 1, psi 2, psi 3, psi 4, psi 5, psi 6, psi 7, psi 8, like we can say like this. Yes or no? Where will be the value of, okay, if you say from here, then you can start theta is equal to 0, theta is equal to some 30 degree or 45 degree. Here you can say like theta is what, 0, here theta is what, 45, here theta is what, 90 degree, okay, here theta is 135, like that you can mention. Where will be the potential function? So potential function you will get perpendicular to this stream function. So how you will get perpendicular? Perpendicular means this should be like this. This is the perpendicular. So basically this is what? This is what? This is what? Circle. So here this is what? Phi 1, phi 2, phi. So this is what? These are the equipotential line and these are the streamline. So this is the flow pattern for the source. Okay. Similarly, if I want to draw, what is the psi you got for the source? You got psi source is q upon 2 pi theta. So this is what source. Okay, and what phi you got? You got q upon 2 pi ln r. So what will be the sink? Sink psi will be what? Minus q upon 2 pi theta. I told you that time only, sink means q will be minus only and phi will be what? That's all. So same thing you can draw for the sink also. It's only the simple thing. Okay, if I say you draw the sink, so definitely sink you can draw. You can say this is what sink here. Okay, and for this the flow is what coming like this. Where will be the equipotential line? Again it will be like here. So this is what sink and this is what source. Okay, this is what equipotential line. Which one? Red one. Let me correct this. Red one, sorry, blue one. Blue one is the equipotential line and this red one is what? Streamline. So what is the difference? Difference is what? Here flow is what? Inward for the sink, and for the source it is outward. That's the only difference. So I hope today what we have done, it is like completely all understood. Thank you all. Thank you so much.